All right, stats. Today we're going to do two lessons, 6.3C and 6.3D. We're just continuing 6.3. Talking about geometric random variables and their distributions. Let's get started. So I know there's a lot to read, so take your time and read it. But basically, we're still dealing with binary trials. So possible outcomes, success or failure is what we're looking at here. Okay. And the difference between what we talked about before, when we're talking about a geometric setting, is we're counting the number of trials until a success occurs. So before, when we were talking about binomial variables, we're talking about we already had a number of trials and how many of those trials are successful. Now we're just going to keep going until we get a success or until we get a failure, one or the other. Okay. Are they independent? Meaning the trials, knowing the result of one it has no effect on the next trial. Okay. The goal is to count the number of trials till the first success, and on each trial, again, our probability for success should be the same. Okay, think of flipping a coin. How many coin flips until we get a heads? Okay, so geometric random variable. So now we're using the letter Y. It doesn't matter what letter we use here. Okay, so the number of trials until we get a geometric random variable. This is the variable, is how many trials until we get success. And we're going to have a geometric distribution with parameter P. And the number values of Y are always, they're discrete because we're counting trials. And it's always right skewed. So when we talk about our shape, if you recall, a right skew has a tail on the right hand side. So if I'm doing this, it's going like that. That was not ideal. So this is our right skew. This is what the distribution should, in theory, look like. So we have a scenario. Please pause and read it so you can follow along. So here we've got some students in a class. They're guessing the day of the week of the birthday. So it's not the date, it's just the day, okay, Monday through Sunday. So we're asking how many guesses until we get a success. So what's the probability there? So first we're testing, can we use a geometric random variable? Is this appropriate? So success, is it binary? Success is a correct guess, failure is incorrect. Are they independent? Does one person's guess, does it have any effect on another person? Well then, the thing that makes it independent is that when one person guesses and they get it wrong, she selects at random another student and then changes to a different friend, which is weird. This is a strange activity, but for the context of the problem, I think it just makes sense. Okay, and then so for T, we're counting the trials. We're counting the number of guesses, and then on each trial, the probability of a correct guess is 1 out of 7 because that's how many days there are in a week. So we're good here. We can use a geometric random variable. So the probability that they'll get it on the first guess is 1 out of 7 chance. So here's your probability there. The probability they get it on the second guess, well, there's 6 out of 7. That's a probability of guessing wrong on the first attempt. And then the second attempt is success, and that's 1 out of 7. So here we have our probability there. What's the probability that they get on the third guess? So here are the two first and second guesses. They're wrong. So they have a 6 out of 7 chance to be wrong on the first one. Same with the second one. And then here's your success. So take a minute and look at what's happening here and see if you can write a general rule for this pattern. So what you should have got is that you have the probability of a failure, and you raise that to the k minus 1 power. It's not here. K is 1, so 1 minus 1 is 0. And then you have multiply that times the probability of success, and that's to the first power. So it's basically 1 minus p to the k minus 1 power. Multiply that times p to the 1. So here's our rule. It is in the formula sheet. So let's do some more examples. Here we got Monopoly. You're in jail. Anybody play Monopoly? One way, if you've ever landed, like, go to jail, go directly to jail. The only way to get out is to roll doubles. So 1, 1, 2, 2, 3, 3, and so on two sets, on a pair of die. Okay, so you're rolling 2 die, and they both need to be the same. The chance of that happening is 1 out of 6. So what's the probability it takes 3 turns to roll doubles? So we need set D is the number of roll as a variable, as the number of rolls to get doubles. It's geometric. We know we either succeed or fail. It's independent. The first roll has nothing to do with the second roll because you pick the dice back up and you shake them and mix them up. We're counting the number of trials till we succeed, and we know the probabilities. So if P is 1 out of 6, that means 1 minus P is 5 out of 6. And we have K minus 1, so K is 3. So we have 2 to the second power, and we multiply that times 1 over 6. That's going to give me 25 over 216, which is about 0.1157. So there is a calculator function for this. See if you can find it. It's in the distribution menu of your calculator. So pause and go find it. There's the command for your calculator. All right, now find the probability it takes more than 3 turns to roll doubles and interpret this value in context. This is a little more likely, right? Because we're looking like, oh, we don't want to go longer than 3. So what does this look like? Well, I wanted to erase that. Shucks. Chucky darn. There we go. What are the chances it takes 4? And then also what is the chance it takes 5 rolls plus and forever, right? What is this starting to look like from previous examples? Well, we can rewrite this as it's 1 minus the probability that D is greater than or equal to, less than or equal to 3, right? Because subtracting this, because this is P in totality here, I would have all of them. Sorry. And I'm subtracting out these to find this. Okay? And all these add up to 1, even though it goes to infinity, they sum to 1. So this is just going to be 1 minus geometric PDF of P equals 1/6, X equals 3. Or excuse me, sorry. Less than or equal to 3, so you just need to do... It's early still. Sorry, it's CDF. P equals 1/6, X is less than or equal to 3. So you're just going to put 3 here. This is cumulative. So we're looking at in our graph, it's skewed right. Maybe it does this kind of thing. We're just taking this and subtracting it out to find this, okay? This is going to equal about 0.5787. So in context, you would write, there's a 57.87% chance that it takes more than 3 turns to roll doubles in Monopoly to get out of jail. Next, we have our center and spread, basically our mu and standard deviation. So, okay, here's the mean. All right, and here's our spread, essentially our standard deviation. What this is saying is that to find the expected value, the mu of y, our geometric random variable, you take the reciprocal of the probability, so 1 over p. So from our Monopoly example, how many rolls should we expect? Right? Well, E of D equals mu D equals 1 over p. P equals 1 over 6. So it's 1 over 1 over 6 equals 6 rolls. We would expect about 6 rolls, 6 turns, okay? So how far the values of the numbers typically vary? Well, S of D equals the square root of 1 minus our probability divided by our probability. Let's fill these values in. Square root of 1 minus 1/6 over 1 over 1/6 equals square root of 5/6 over, don't need fractions anymore, times 6 over 1 equals 6 times 5/6 under the square root. And that's about 5.477 rolls. So our graph, we got this number here. So let's say this is 6. That means our spread is kind of taking up this space here, right? This is how much typically the average distance from the average. That's one way to look at it.